Good evening, ladies and gentlemen. Thank you for having me today. I am grateful to organizers to give me this opportunity to present our results. Today I would like to show you our recent results on detection and manipulation of single superconducting vortices in simple nanostructures. Using our nanosecond resolving thermometry developed in recent years in our laboratory, we are able to measure the heat dissipation due to expulsion of a single vortex out of the superconducting nanostructures. In the title of this presentation we mentioned the quantum thermodynamics. How do we understand this? So the quantum thermodynamics deals with the heat transfer, investigation of the heat transfer for the single particle level. So if you measure the heat transfer approaching the quantum limits, then we can talk about quantum thermodynamics. Here I have a few examples. In this first experiment, authors measure the heat transfer through the single phonon mode channel in such narrow necks. Okay. In this experiment, authors measure thermal conductance approaching quantum limits between two metallic islands, and it was mediated by photons. And in this example, it was measured heat transfer to the single electronic channel, not channels, excuse me. For last years, we were trying to investigate the fast thermal processes in very general, I mean hot electron diffusion, electron phonon coupling, and this time we focus on the moving vortex. And okay, so we extend the notion of the particle to vortex, because vortex is well defined, is quantized, and is topologically protected. So in this context that I present, we can talk about the quantum thermodynamics of a single superconducting vortex. Okay, so in order to trap and detect single vortices, we designed and fabricated such simple structures. Compared to your structures, typically it looks very modest, yes. So it consists of the trap in form of square. There is a dime nanobridge in its vicinity, and everything is connected through the narrow leads to the contact pads. It's made from 30 nanometer of polycrystalline aluminum. Of course, it's a single-step lithography. We cool down this nanostructure below TC, and we apply the perpendicularly applied to the surface of the trap magnetic field. In order to understand the vortex behavior in our nanostructure, we consider Gibbs free energy across our box. So for low magnetic fields, there is no stable conditions to trap the vortex, but when we increase magnetic field, at some moment we can see that there is some minimum developed in the middle of our trap. So starting from B0 for larger magnetic fields, we can capture the vortex inside, and this vortex position is stabilized by Bean-Livingstone barriers. We can also send some current pulse to our nanostructure. So when we apply this, we can tilt those potential energies, and at some critical moments, expulsion current, the minimum of this Gibbs free energy disappears, and vortex is no longer welcome in such structure and runs away. Okay, so now let's introduce switching measurement. Today I will just give you only summary because it's quite long, and on next 2 days Maciej Zgierski in his talk he will just give some more details about this switching. But in very general, we exploit the ability of the dime nanobridge of the switching from superconducting to normal state. Particularly, we take advantage of temperature dependence of this switching. So whenever you see in your system heating, then you will see suppression of switching current. In the opposite, if you measure cooling, switching current will increase. In this method, we send train of pulses to our bridge. So first pulse is reset pulse. Its amplitude is higher than switching current of the bridge. So we apply this pulse, we overheat all the nanostructure to normal state. In this moment, the trap is uniformly penetrated by
magnetic field. When the reset pulse is over, everything cools down through the electron-phonon interactions. And when we pass DC, and magnetic field is strong enough, we can capture the single vortex into our trap. Afterwards, we send another pulse. It calls testing pulse. And intention of this pulse is to measure switching current of the bridge for the switching probability equal half. So we send typically send 1,000, 10,000 of such cycles to our bridge to determine the switching current of the bridge. And every cycle for this experiment consists of reset pulse and testing pulse. Okay, here are first measurements. Okay, so we measure the switching current versus perpendicularly applied magnetic field. For low magnetic fields, you can see parabolically suppression of the switching current, which we associate with Meissner screening current's influence on the order parameter. At some moment, you can see there is some suppression of the switching current, and so again, taking into consideration the Gibbs free energy, we expect at some moment first vortex entry, and it even gives very similar value with our experiment. So we associate this value, this B0 value, with the first vortex entry. So okay, how it looks in more detail. So when the reset pulse is over, so we are just starting from normal state, we are cooling, we are trapping vortex. Afterwards, we just achieve bath temperature, and at some moment we send our testing pulse. And as you already know, that by sending pulse we can tilt this potential and we can move out the vortex. Moving vortex is a source of dissipation. So it creates quasi-particles. Yes, so there are all around quasi-particles. Those quasi-particles reaches also our bridge, and it suppresses the switching current. That way we see such dip. Okay, so we also measure this B0 value, so the magnetic field at which first vortex enters into trap, also for different nanostructures with different H value. And as you can see, there is very nice relation between this B0 and 1 over W square, and also it falls on the theoretical prediction with this simple formula. Yes, so we can, in other words, we can engineer our structure, we can design it, and we can just plan very precisely when the vortex will enter into your trap. Okay, so let's go back to our measurement, and now let's focus on the region of the first vortex entry. Okay, red curve is the same measure again with better resolution, but blue one is the same curve, but here we add new pulse. So after reset pulse, after some time, we added we call this Lorentz pulse. So this intention of this pulse is to expel the vortex, so act with the Lorentz pulse on the vortex, exert the force, but not to switch the bridge. So in such situation, you can see that by applying 5 nanosecond Lorentz pulse with amplitude 120 microamperes, we can extend the Meissner state to higher values. So in other words, we can recover no vortex state in the region between B0 and around 5 millitesla. Okay, so and as you can see, the vortex presence is manifested by low switching current, and vortex absence by high switching current. Okay, so now it's time for another experiment. Let's fix the magnetic field at 4.6 of millitesla, and now let's measure the structure in a function of Lorentz pulse for both of polarizations. So for low amplitudes of Lorentz pulses, generally we are not able to expel the vortex. So after 40 microseconds, when we send another pulse, we read the system at a low value of the switching current. But if the Lorentz pulse is strong enough to expel it, after 40 microseconds, okay, testing pulse finds this in the high switching value. If the Lorentz pulse is even higher, it of course moves away the vortex, but additionally it also switches the bridge. That way, this high Lorentz pulse also acts as a reset pulse. Yes. Okay, so we also made such measurements for the other magnetic fields. When we collected, we obtained such very nice map, which we called vortex stability diagram. And as okay, so on here we have on the X we have Lorentz pulse. Here we have magnetic magnetic field, and colors represents to switching current of the bridge. For low magnetic fields, we are in Meissner state. So okay, there is no effect of Lorentz pulse because expected, yes, because there is no vortex. But when for higher magnetic fields, we can capture the vortex. Not only capture, as we can see, but also we can manipulate it. So this diagram gives us full information about the current that you need to apply to your structure to precisely expel the vortex at given magnetic field. And if we again use our Gibbs free energy, it also this tells us that if the magnetic field is stronger and stronger, the minimum is deeper and deeper, which means that vortex sits more stable in the nanostructure. That way you need larger amplitude of the Lorentz pulse in order to expel it. And as you can see, okay, we see this clear relation in our experiment, okay, here by this relation between this expulsion current and magnetic field. Okay, so now it's time to implement our nanosecond thermometer to measure thermal effects. So we pick for these 2 points. Number one is in Meissner state, and second one is in the region when we expect vortex presence in our box. Okay, so we send Lorentz pulse, we expel the vortex, and we measure the temperature, electron temperature after the expulsion of the vortex. And here you see that directly after expulsion vortex, after first nanoseconds, yes, we have first nanoseconds measurements, we see some obvious temperature increase. This is really substantial increase, more than 200 millikelvin. But remember here that the process of the vortex expulsion in accordance with literature and in accordance with time-dependent Ginzburg-Landau simulation performed by our colleagues from Antwerp University is much faster. So it reaches tens of picoseconds. So of course it is out of the range of our thermometry, but fortunately for us, this living vortex, this leaves also the thermal fingerprint. It creates quasi-particles, and quasi-particles they decay within a reach of our thermometry. So you can see that this relaxation of this box, of electron temperature of this box, is exponential with time of 400 nanoseconds, which fits very well to our previous measurements about the electron phonon relaxations time for such structures for this temperature. Also, I put here this point number one in Meissner state, and as you can see, there is no effect, no thermal effect, although we send some similar value of the Lorentz pulse amplitude. Okay, so having those results, experimental results, with these calorimetric results, we can calculate the energy of the single vortex expulsion. Yes, so we use for this specific aluminum specific heat taken from literature, and also the temperature measured in our experiment. And we got this heat as a 4 multiplied by 10 to minus 19 of joule, which is energy of the single visible photon. We can compare this with some theoretical model in which we assume that viscous flow of the vortex. So okay, we assume that leaving vortex, when it leaves this trap, it destroys all Cooper pairs on its path. So we can calculate the number of these generated quasi-particles as a product of density of states at Fermi energy, the generated volume, which is marked here by this violet belt, and the superconducting value. And so we can see that this theoretical value is very, very close to almost the same. But of course, remember that there is some uncertainty. Uncertainty comes from the poor knowledge of specific heat and also the heated volume. Yes, this is the problem. Okay, so all those efforts were done in the laboratory of Kulfon group, the Maciej-Zgirski group, at the Institute of Physics, Polish Academy of Sciences. And we have a long and fruitful collaboration with our friend Alexander Savin, which also helped us a lot. So I'm also part of this Kulfon group, and Konrad Orowski, PhD student, also involved in this experiment. Okay, so thank you very much for your attention.
Yeah, thank you very much.
Marek, could you show the previous slide, please? Again, once more. Yes.
Yeah.
Here, n is a number of quasi-particles.
This one?
Yes.
This is number of quasi-particles generated.
Yeah.
Yes. So when your vortex is living, okay. So we have this volume, this dimension multiplied by the thickness. Yes, and in this volume, okay, we just assume that all Cooper pairs are destroyed, and okay, so.
But the condensation energy is 1/2 g per unit of volume, 1/2 g delta square.
Okay. I will double check this.
Yeah, so it is double delta squared, because then, as you see, it's when we
it's
heat
already divided by delta.
heat is then multiplied, NQP is multiplied by delta.
Yeah, okay, good.
So together it's
Now I got it. Thank you.
Thank you. There was a question here.
What's the frequency and dissipation of the vortex oscillation in the graph?
Okay.
In a resonant way?
This is we are sending pulses. Yes. So okay. So frequency. Okay. We can somehow say about this, but okay. This is situation that we have stable vortex. We send a pulse and we just move it. Yes.
Can you do it resonant?
We can, but afterwards we can't use our nanosecond thermometer, because okay, first of all, this thermometer addresses perfectly repeatable processes, so we need also to repeat every cycle. We need to repeat the same. Yes, in every cycle, vortex must be expelled, and only in such situation we can use our thermometry.
Yeah, please.
Thank you for the presentation. As I understand, you calculated only the energy of the quasi-particles.
Excuse me?
As I understand, in this calculation of energy, it's only quasi-particles.
Yes.
What about the energy of the current circulating around the vortex, which is also...
Current circulating around. Okay, we just took the.
Are they neglected, or?
Of course add this. Okay, this is as you can see, this is quite simple model. So of course it could be built up. This is just comparison with first assumption that okay, we just take into consideration only the energy of Cooper pairs. Yes, of quasi-particles, excited quasi-particles. Yes.
Yeah.
Very just technical question. You use rather short pulsing sequences, like nanoseconds?
Yes, this is increased time in our. Of course, we can improve it, and this is one of our aim. But so far, we didn't. This increased time is around 2-3 nanoseconds.
Okay, but do you use is that structure embedded in a transmission line, or?
It's connected. Yes, it's connected from the generator. From the generator to the fast lines, it is directly connected to our structure. One of the contact pads. Second one is grounded.
Okay, so it's on chip also a transmission line.
Yes, it's okay. This is a relatively slow frequency, so I don't know if we can say this. Contact paths are rather large, and the structure is something like 40 micrometers. So this is just very narrow line. So okay, this is.
Okay, so if there are no more questions, I think we can thank Marek and all the speakers again.
Thank you very much. Thank you.